Welcome to APEC. It's February 13th, and I'm your moderator, Tim Ventura. First, I'd like to thank everyone for joining us on this call, along with everyone watching us on YouTube. We have a big session for you today featuring WARPA founder and former Airbus VP Jean-François Geneste, along with Boeing engineer Mike Gamble on gravity modification. We also have the infamous Jeremy Rys, aka Alien Scientist, who will be presenting on metamaterials and materials engineering. This week, we're going to mix things up just a little bit, starting out with a half-hour lab update from Mark Sokol and the Falcon Space team, who are going to walk us through the tremendous progress that they're making on their many experimental projects. So just a couple of quick announcements. Our new website is now online at www.altpropulsion.com. Again, that's www.altpropulsion.com, and you can always view our conference events on American Antigravity or on Alien Scientist as well. Please save your questions for the Q&A session after each presenter finishes. Please type your questions into chat, and we will go through them after each presenter wraps up their presentation. So without any further ado, let's hand things over to Mark Sokol and the Falcon Space team.
Okay, thank you very much, Tim. We're here at the lab in Hawthorne, New Jersey. There's going to be an update from this lab, from Jeremiah's lab in Milwaukee, and also Todd Desiato down in North Carolina is going to be giving us an update as well. Hopefully we have enough material to fill half an hour because there's a small progress on each little experiment that we're working on. Of course, the big experiment that we're working on is the Alzaphan experiment, and there's two variations of it. There's the dynamic nuclear orientation using a laminar magnetic field, and the microwaves, which hit the electrons at the Larmor precession to orient the core of the atom. And for that, we needed to build a microwave tuned microwave cavity chamber. We sent out the copper to the machine shop, and it came back. It needed to be polished, so that's something that I've been working on over here. We're trying to get a mirror fine polish on it. We're going to probably be soldering it together. And then there's going to be a plate at the end that can move in and out, so it's tunable. And then we can detect whether we're reaching resonance or not. Now, the way we're going to know if we're reaching resonance is through this device over here. This is, of course, a klystron. It is powered by this 5,000 volt half amp power supply that Jeremy hooked us up with. This is our signal analyzer, and this over here, these are power meters that hook up to these cross guides, which tell us the forward and aft power, so we can know when we're getting reflections back and how much power we're actually pumping into the chamber, and how much is coming back. Over here, we have isolators, which are basically one-way tubes for, like one-way diodes for waveguides, and then beyond that is a tuned waveguide piece that's tuned precisely to 6.28 gigahertz. So it has almost little tuning pins inside of it. And that was also picked up by Jeremy from the same place. So that is the update on the high power version of the Alzaphan experiment. And we also have another version of the experiment that's based off of Mark Sokol ARV. And I showed this to David, and he said that he actually showed it to his dad when his dad was alive, and his dad mentioned that this would also create dynamic nuclear orientation. And the coils over here are being pulsed by the high voltage capacitor in the base. So we call this experiment Easy Alzaphan because this is a lot easier to achieve than the whole microwave system. And here is our first attempt at it. And for everyone who watched my YouTube videos on this, there was many problems with this setup, and it started to make sense why that diagram had the coils inside of glass, because when you apply a high voltage to these, and this is a sinusoidal high voltage, so it's a high voltage peak one way and it's going back the other way, and we're using a spark gap to make that happen. These are the high voltage capacitors, by the way. But when you pulse it with high voltage, and we're talking about like 10, 15,000 volts DC, or AC actually, the coil, because they're not really well isolated, was sparking to itself. And the very thin isolation material that we have over the wire was completely insufficient. So we needed to make a new coil. In further talks with Todd, who's also on our team, Todd Desiato, who will be presenting next. He mentioned that if you had one side of the coil longer than the other, it would produce a some sort of effect. And that's when I looked at the ARV picture again, that's exactly what I saw. You see one side of the of that coil over there is slightly longer than it's longer on the base than it is on the top. Jeremy Rys came down here after his interview with Tim Pool, and he helped us build this over here, which is, I don't know if you can see it very well, but that is chock full of electromagnetic wire, and it is in the exact same shape. We still have to fill it up with epoxy and stick it inside the vacuum chamber to suck out all the holes. That's the next step that I'm still working on. The epoxy that we have for that is epoxy cast 690. It's a 2-part epoxy, supposed to be extremely thin, and we'll be able to pull all the air out, and hopefully we'll have a electromagnet that will work with the high voltage. And that's pretty much the update from the lab. I think, Todd, do you have anything?
Hey, is Todd there? I'm not sure if Todd is with us. I believe Jeremiah is here, though. Jeremiah, do you have an update?
Yeah, I've been crazy busy, but I'm not feeling well at the moment at all, and I'm way behind. My camera decided to glitch out and destroy itself or something like that, my regular point and shoot. So all the pictures that I had on there may be corrupted on the memory card, and that was kind of unideal to have happen, right before I was about to do a set of pictures. I guess I can show a few things here. So I have been quite busy making a variety of different dot product discs for the Banderic experiment, and these are some of the newest iterations. I tested the amount of charge that I could store on a copper disc equivalent to these things. They're 5 inches or something in diameter, thereabouts. And I'm able to store about 15 volts on a 1 microfarad capacitor with just solid plates. And so I can get an additional 3.5 volts on that capacitor with the addition of this this material here, which is about 5.2 millimeters thick, which basically means that the charge is being stored inside of the disc itself. It's not being stored on the surface like a regular capacitor plate, because this increases the capacity of the system. The charges are actually leaving this. The electrons are coming out of this disc here, leaving it positively charged. And because there's so much copper mass, there's so many free electrons to leave, it allows the negative disc, which is solid, to really be charged up. So that's been good. We actually are getting significant increases in the complex field components from these discs, which is really, really nice. And they're pretty balanced, so I may actually try to spin this up at maybe some 5,000 to 10,000 RPMs just to add that little bit of extra, because I can't really take the cross-product discs beyond 15,000 RPMs without reaching instability problems or being concerned that the G6 might, blow out. We also have, through these guys together, there's some fun. I've always wanted to build these Boyd-Bushman magnetic beamers. So Boyd-Bushman has a patent about a magnetic beam generator that can shoot out a beam by modulating it with a electromagnetic coil, which is effectively what this is. Now, I didn't try to modulate these back neodymium magnets directly because they're effectively conductive, very conductive, in fact, and they'll short out any eddy currents that you wrap around them if you try to wind a coil around these things directly. I could use ceramic magnets, which won't suffer that problem, and I may very well go to that. But for now, I'm just trying to disrupt the field linearity that goes between this back magnet using this small coil and the rest of the magnetic assembly, and then I should be able to detect it very well with this. So I haven't had a chance to hook this coil up to the scope yet. I am capacitor discharging into this coil here with a 1 kV capacitor, 1.1 microfarads. And so to pair with that, on the other side, there is a second beamer. They actually face together like this, so that the rear magnets are facing apart from each other. And they should establish a connection which is easily broken by modulating that field with either this coil or the other coil. And then, of course, we also have un momento. A lot of force to try to pull those things off the bar. Because Ziggy's big old magnet experiment. So these are the 2-inch diameter, 1-inch thick N42 magnets that I got for the big news. rotating field experiment. Oh yeah, very much so. I have this thing shockingly close to my computer. I have to be careful which direction I point it in because I just took a small neodymium and hung it from a string, and from about 4 feet away, the thing is strong enough to polarize itself, or when you release it, it almost instantly pulls itself straight. It doesn't really even bob back and forth. So these things have a hell of a field extending out from their poles, at least 4 feet. And if you measure the weaker field, with the compass, you can pick it up from 9 or 10 feet away. So that's pretty good. And now these will have to rotate at least 4,000 RPMs. We're going to try to hit some 7,000 if that's possible. But we'll see. Building the capacitor part of that system too, those magnets are going to be wrapped in an axial capacitor that's wound around it. So there'll be a solid piece of dielectric that surrounds those magnets, and then entrapped within that dielectric will be another electrode, which will be charged up, and then the entire system spun. And so what we're hoping is that the electric field of the rotation being, produced under that strong B flux will have some kind of either propulsive effect or weight loss that we're looking for. It should pretty much simulate sort of like the rotating dipole moment of an atom. So that's what we're going to find out pretty soon here. There are lots of little experiments that we have going on in the interim that are sort of pieces of larger experiments, wireless charging, so we can isolate systems, or wireless power regulation into some of these circuits. I want to power the tubes with a wireless interface via coil so that I can send at least 25,000 volts of isolation. And the reason why I want to wirelessly operate the tube filaments instead of having them run off batteries is because it'll allow me to have multiple tubes in series, so I can get a higher rectification voltage off those things without having to worry about changing multiple batteries or triggering multiple circuits. That pretty much covers what I have going on in the immediate that's ready to show. I have a lot of stuff that's not ready to show that I can't just pick up and stick in front of my webcam. I wish I would have had better pictures to kind of show off, the high voltage power supplies and all that stuff, but things happen. Doesn't always go as planned. So that's the basic what I can show you for now from the Wisconsin lab update.
Wonderful. Well, Jeremiah, thank you. And let me see. So we can go back to Mark, but we do have Todd here. Let me ask Todd to unmute.
I'm here.
Wonderful. Wonderful. Okay. And let's try the screen share now.
All right. Nope. I don't need it. That's all right.
Okay.
Hey, so over the past couple of weeks, I've been working on my NMR experiment, and I'm going to move aside so you can see the picture behind me. I have the on the little circular plate there is my NMR board that I designed, which has the bandpass filter, and then next to it there is a breadboard with a teensy 4.1 microcontroller. The teensy is a 600 megahertz microcontroller that has 18 analog inputs, but I'm only using 2 of them at a time, so I can sample at 25 kilohertz. So that gives me plenty of bandwidth to record the Earth field NMR signals directly into RAM and put it on an SD card or into a spreadsheet. And I can also look at it in real time with this, just like an oscilloscope. But with it, I can simultaneously measure the magnetic field strength as well as the signals from the NMR. And that's the goal, so I could get everything self-contained. And if somebody wanted to replicate the experiment, they don't need an expensive oscilloscope. So I basically put this together, and then you see to the left over here is the zero Gauss chamber. And so that's got my Helmholtz coils and my gradient coil and my sensor inductor, and all that's powered through the board. And this power supply over on this side, and the power supply there, I've got 2 potentiometers that give me the ability to very finely control the magnetic field of the Helmholtz coils and the gradient coils.
Todd, sorry for jumping in. I have screen sharing enabled if you want to do that now.
It looks fine. I think it's good. It's the same picture as all I wanted to show. So that's what I have. So I spent some time programming, but most of the time I was working my day job. I have a startup solar company here in North Carolina, and we finished our first solar project. So I was passed inspection, everything's done. And so I was real happy about that, but it kept me busy for the last 2 weeks. So that's pretty much it. The next goal is to start putting in some samples. And well, first I'm going to characterize the magnetic field and record that data. And then I'm going to start putting some samples in and see what we get. And that's pretty much where I'm at now. So hopefully in the next week or so, I'll have some data.
Wonderful. Thank you, Todd. Thank you. Okay, so let me see. I'm going to remove Spotlight there. Okay, and let's go back to Mark. Mark, do you have a little bit more to share?
Yes. So Mike Gamble was going to talk about the gyroscope experiment. He asked me to show him our gyroscope setup. So this is the device I built. And it's basically 4 gyroscopes. They're all spinning. On this side, they're spinning clockwise. On the other side, they're spinning counterclockwise relative to the motor. So we had to wire the motors backwards. They are the same gyroscopes that he is using. And I checked them with an RPM meter. They are moving at around 20,000 RPM each. They have the degrees of motion of freedom are 90 degrees forward and to the side, and then 90 degrees vertical. So where you're basically taking off a quarter of or an eighth of a sphere, you would call it. This is all remote controlled via a RC controller, a programmable RC controller. So I could literally do any movement that is within the constraints of these servos and the servo setup. You can see over here, I have the servos mounted off to the side for the x-axis. For the z-axis, it's literally directly on it. This is the standard setup that you'd have in the pan and tilt setup for a FPV, camera on a drone or something like that. This is the 3rd iteration of this device. We have ran it a couple of times and have seen some anomalous results. I do believe there is a connection between angular momentum and linear motion. And if we can prove that, then that would also explain where inertial mass comes from, because if you think about it, the core of the atom is literally just a whole bunch of these gyroscopes with complex spins. So if you're moving something around, if you're moving an object, then you are going to change their spins if there is a connection between linear momentum and angular momentum. So that's why I think this is a very important experiment. Another experiment that we were going to try, which is similar to this, is the, we call it the Vimana, or the rotating mercury. Jeremiah over there in the Milwaukee lab has about 20 pounds of mercury available. I have a couple of pounds over here as well. We plan on setting up a negative flow hood chamber near the window right behind me, and we're going to work on mercury over there. We're going to have tubes set up and basically a linear motor in order to push the mercury through it. The question is what shape to make the tubes and how exactly we are going to build that. So if anyone has any input for that, that will be helpful. Also, getting back to the Alzaphon experiment, we are in search of an NMR or an EPR electromagnet. If anyone knows anyone for any unit for sale, we do have a budget, and we're looking for something with at least a 3-inch cubed space of with about 1 Tesla. And the ability to do NMR, EPR, like a very homogeneous field. So if any of the universities that you're in contact with has an NMR or EPR magnet set up for sale, just shoot me an email at falconspaceprogram@gmail.com. We have seen one on eBay, but we are kind of concerned that because of its condition and its size. So if anyone knows anything, hit us up.
Yeah, and speaking of requesting information, I am looking for assistance designing a churro split ring resonator array. I have an idea about the frequency range that I want to run in. I'm mainly concerned with what kind of driving frequency I can get away with and still get decent coupling, and how I want to interface with those rings. So if anybody happens to be an expert on metamaterials or knows something about metamaterials and might be able to help me design a split ring resonator array, I could certainly use the help. Please feel free to email me at exoticpropulsion@gmail.com. And hopefully we can go from there, and I'll fill you in on some details about the experiment. Thanks.
Wonderful. Thank you, Jeremiah. So actually, we did have a question. It looks like we have a couple of minutes. Paul Murad has been raising his hand. Paul?
How you doing? When you fool around with this mercury, you're going to stick any barium titanate in there?
Somebody actually once recommended that, and I actually have a little pill jar with mercury and barium titanate mixed together. I have no idea what I'm going to use it for, but I have some. Why would you recommend we do that?
It's going to give you some nice effects.
Okay, well, I already have some. Well, what kind of effects will happen, and what do I do with it?
You let me know.
Well, we're wondering, like, how do we run it? Are you saying just rotating or circulating mercury with barium titanate mixed in it is enough?
Do
or
it,
do we
I'll
have
tell you
to...
what. Do it both ways. Run it with no barium titanate, and then run it with barium titanate and see what happens. Okay.
That'll be interesting.
The question here is, I don't know, you guys are a bunch of young guys, so
Here it is.
I don't know anything about it, but
There it is. Literally, barium
heard of,
titanate and mercury.
okay, have you heard about red mercury?
That's what barium titanate and mercury looks like.
Okay, but you know, the thing is that certain stuff in there, like ending up with red mercury, that goes back to World War II and a lot of rumors, and you know, there's got to be some effects there. Okay.
Yeah, I would assume that it's some sort of ferrous metal that doesn't amalgam with copper, with mercury, because you want to keep the mercury liquid, but you still want to move it through the MHD, and mercury is not a very ferrous material to be moving through an MHD, so throwing like little powdered iron or any material that wouldn't amalgam with
ferromagnetic fluid or anything like that. That's what you're looking for. Okay.
Yeah, but it needs to not amalgam with the mercury. That's the concern.
Okay.
Well, let me mute. Thank you, Paul. So does anyone else have any questions really quick? We've got about 5 minutes left. And let me see, anybody else, any questions for Mark about the lab updates? You guys have a lot of experiments going, so.
I would say one other thing, that if you could also reach me at altpropulsion.com, altpropulsion@gmail.com, the email that the invite is sent out from. So if you have any links or anybody selling an NMR or EPR electromagnet, you can just reply to the invite, and we'd get that information directly.
Oh, and it looks like, let me see, Michael Richardson might be raising his hand.
Oh, David Alzafon said something as well.
Oh, okay. Let me see. David was asking about waveguide design. David, let me. You can unmute yourself if you like. There we go. Ask to unmute.
So the waveguide design right now, we're just going with the wavelength, for width and length. The wavelength being, the length of the actual gigahertz wave, and it's going to be short, sort of like a square, a rectangular shoebox design. So the waveguide piece is coming in, and it cuts off at a 90-degree angle into this box. That's what was suggested by Tanya Slowetsky. I'm not really sure how to pronounce her last name, of the Penn State University, who works on similar projects down in the 2.4 gigahertz range. So that's what we're doing over here for the X-band and for the C-band version of the L-SPAN experiment.
And David, you're unmuted, so go ahead, sir.
Oh, I don't have anything to add. I know that Mark was seeking some advice about construction of the waveguide so as to achieve dynamic nuclear orientation. And that's one part of the design that I couldn't relay because, well, actually somebody contacted me and said they would work with my dad, and they didn't want me to publish that. So I've had to keep it reluctantly close to my vest, but it it seems to me that the design that he used could be improved on. It wasn't a huge hump, but as long as there are all these people out there in the audience with that technical expertise, it seems that you should be able to get a good waveguide design for the experiment.
Yeah, what's really important though is to make sure that you have really smooth surfaces. Like over here, you can see the my reflection off of this copper. This was several hours of work to polish each one of these. You need to have literally mirror perfect polish on the copper, and it needs to be similar dimensions on either side, and you need to have a way to know when it's tuned. If it's not tuned, it's not going to work. You'll be shooting energy right back into the source, and that can also break your amplifier, in this case the klystron. So all the ancillary equipment are also very important to figuring out what you're looking at. And we're also going to plate this in silver. Once it's complete, we'll plate it with silver. I have a special silver plating polish that we're going to put on it, because silver has a higher Q factor than copper.
I have one more question, Mark, and that is, are you going to be able to tell whether or not dynamic nuclear orientation is taking place? Can you measure it? Is there any feedback you can get that will tell you it's happening?
I'm not sure about that. That's something we're going to have to look into, if there's any way to see that, because we're doing a pulsed version of it, and maybe there is some sort of feedback that you'd get when the pulse is off that we can read. The problem is also anything that you're putting inside that chamber is going to be receiving a ton of RF during the on phase. So how are you going to be able to read the off phase? Like, the difference in power ratios is going to be tremendous. So it's both a mechanical problem, a technological problem, and a physical problem of whether there is even a signal that will be coming out from the relaxation time.
Okay. So we are at 11:58. We're a little bit early. Mark, do you have any last thoughts before we transition over to Jean-François?
No, go for it. I'm
okay.
good.
Well, thank you again, sir. And just kind of a notice for everybody, Mark and the Falcon Space team will be here for the entire conference. And if you have more questions, I'm sure you guys do, they will probably be able to answer all of those later on in the presentation. And Jeremy Rys will be doing a presentation as well, so he'll be able to touch on some of these things, hopefully, as well.